we're going to go over problem number 3 from the Thermochemistry Quiz. This problem is a calorimetry problem, but it also involves a phase change where we're melting some ice. In this problem, you were given the reaction for the heat of combustion of isopropyl alcohol, and in part A, you were asked to calculate delta H for this reaction, and most of you successfully did that by using the heats of formation values from the table. Now don't forget that that heat of reaction means that we generate 4,013 kilojoules of energy for every 2 moles of isopropyl alcohol that react, and for every 9 moles of oxygen that react, etc. So in part B of the problem, this is the calorimetry problem, we are asked, well, we're given this scenario where we're burning 5 grams of isopropyl alcohol, and it's going to melt 145 grams of ice, and then that resulting beaker of water is going to be warmed up to some final temperature, and we want to find that final temperature. So in order to solve this problem, we need to keep track of where all the heat is coming from and where it's going into. One thing that's happening is that we're burning a fuel, so we're generating some heat. This is an exothermic reaction. So I'm going to have some heat that's generated from burning the C3H8. That heat is going to go into melting the ice. So I have another term for the ice melting. Now some of you on the quiz included a term for warming up the ice. But you don't need to warm up the ice before you melt it, because you're told in the problem that this ice-water mixture starts at 0 degrees Celsius. We're already at the melting point of ice, so there's no need to warm it up. You don't need to use the specific heat of ice in this problem. After we melt the ice, then we have a beaker of water, and any additional heat that's left over will be used to warm up that water to some final temperature. So we also have a term for the heat that goes into warming the water. And we're told in the problem that no heat is lost to the surroundings, and so we can assume that all of this different exchange of heat adds up to 0. The way that's actually going to work out is that our combustion reaction is exothermic, so that'll be a negative value. Melting ice and warming up water are both endothermic processes, so the heat involved in those processes is going to be positive. And so our signs should take care of themselves. Negative plus positive, we should get numbers that all add up to 0. Now I have to replace all these Q's with the different expressions that they represent. So the first one, this is the heat generated in the reaction of isopropyl alcohol burning. So it's the reaction that I had in part A. I already calculated the enthalpy change for that reaction. So it's the enthalpy of combustion for that reaction in part A times the moles of isopropyl alcohol that actually combusted. Now I saw in the quiz that some of you use delta H of formation of isopropyl alcohol, but this is not a formation reaction. The reaction that's actually occurring in this little alcohol burner is a combustion reaction. So you have to use the corresponding delta H for that reaction. My ice melting is a phase change. It occurs at a constant temperature, which means that when I replace Q with the correct expression, it's equal to the heat of fusion of ice times, now sometimes it's times the grams of ice and sometimes it's the moles of ice. But if I look at the information I'm given on the handout, it's given as kilojoules per mole. And so that means I'll have to multiply by the actual moles of ice in order to convert that to just kilojoules. And then Q for the water warming up. Now this is a temperature change, so this Q is going to get replaced with the expression ms delta T. It's going to be the mass of everything that's warming up times the specific heat of water, because that's the substance warming up, times the temperature change of water, which is what we're looking for. So that's all got to add up to 0. This is the hardest part of the problem, is setting up this expression. A lot of you put extra terms in for things like vaporization of water or warming up of ice. So be careful not to put in extra terms for things that aren't actually occurring in this situation. Now I'm going to plug in my numbers. The heat of combustion I found in part A, it was negative 4013 kilojoules. And don't forget, that's the energy released for every 2 moles of isopropyl alcohol that burns, not just 1. So now I need to multiply by the actual moles, and I had gone ahead and turned grams into moles earlier just to save some time. But we could do it at this step too if we had to. So that becomes 0.0832 moles. And that's my first heat term. That would be a negative number because it was an exothermic reaction. The heat of fusion of ice, I look up on the reference table. I'm told that that's 6.02 kilojoules per mole of ice that melts. And then I had already converted the grams of ice into moles. So that's 8.04661 moles of ice. Okay, so my moles are going to cancel out. I'll have kilojoules in this term. This term will also be in terms of kilojoules. And now my last term, my ms delta T, I'm going to write it on the next line because I'm out of room here. I need to use the mass of all the water in the beaker. And at this point, the ice has already melted. So now I don't just have 250 grams of water, I have 250 grams plus 145 grams. So that means I have a total of 395.0 grams of water. My specific heat should be the specific heat of the substance warming up. It's not ice that's warming up, it's not steam that's warming up, it's water, it's liquid water. So that's going to be 4.18 joules per gram degrees Celsius. Grams are going to cancel out, but I noticed that I have this in units of joules, and my other two terms were in kilojoules. So I'm going to fix that right now. There are 1,000 joules in 1 kilojoule. And then my final term in this expression was a delta T. T final minus T initial. Well, the T final is what I'm solving for in this problem, but my initial temperature of water was 0 degrees Celsius. That's what I was told in the original problem. So that all has to add up to 0. Joules cancel out. Degrees Celsius is what my units will be in when I solve for T final. And so now all I have left to do is a little algebra on my calculator. And I'm going to write my final answer up here because I'm running out of space. But when we solve for T final, we find that it is equal to 72 degrees Celsius. And so that's our final answer.